People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Since time immemorial, blacksmiths have known that the hotter metal gets, the more it glows. It starts out red, then gets yellower, and then eventually white. In 1900, Max Planck discovered the relationship between an ideal object's radiation of light and its temperature. 120 years later, we're using the consequences of this discovery for many things, including, indirectly, LED TVs. But perhaps one of the most dangerously neglected, or at least ignored, applications of this theory is in climate science. So what is the greenhouse effect? How does blackbody radiation help us design factories? And what are the problems with this model? All of this and more on this episode of Breaking Math. Episode 46, Earth Irradiated. I'm Sophia.
And I'm Gabriel.
And you're listening to Breaking Math. We have a few plugs to go through. We have a Patreon that you can donate as little as $1 to, and we can mention you on the show if you want in your favorite math concept. Or, just like if your name is Emily and you like spiners, we could say like Emily likes spiners. Nobody's done that yet. If you could do the $5 tier where you get access to slightly early episodes when we have them earlier than we are putting them out on the stream. And you also get access to our outlines, which we try to put up every week. And then for the poster tier, it's $22.46, I believe, a month. But if you don't want to pay for that, every month. You could just buy a poster on Facebook at facebook.com/breakingmathpodcast.
Yeah, just to emphasize that. So the Patreon model is a monthly thing. So that's why on Patreon it says, if you give that amount, it's $22.46 per month. But as Sophia just said, if you buy that on our Facebook store, that's only a one-time thing. So you have that option. You have that option as well.
Yeah, and it's $22.46 for a Tensor poster on Facebook, plus $4.50 shipping and handling. You can also find updates about the show there. We're also on Twitter at Breaking Math Pod, and we have a website, breakingmathpodcast.com, which is currently in the process of being renovated.
This is a very, very exciting episode. I know it's been a little while since we've put an episode out. It's been around December. We took some time off for the holidays and to do some research. And Sophia, you've done some really serious research since our last episode, haven't you?
Oh, yeah. Like, I've been doing research into the math behind climate science, because people are always saying, that environmental scientists tend to believe more in human-caused climate change, and so I wanted to explore the reason behind that. And the reason is actually, there are more complicated models of climate science, which we're actually going to talk about on this episode, but even the simplest models are fairly accurate and tell us some very telling things.
Yeah. And real quick, do you mind, before we dive into it, I want to actually mention the sources that you used in preparing this episode.
Oh, yeah. A lot of it is from this resource from harvard.edu. And this resource has some flaws with it. For example, they use when it means micrometers. And it doesn't explain everything exactly well. There's a lot you have to figure out on your own. We're actually going to put out a paper in about a week after this episode airs that explains this a lot better. And eventually we might actually be doing a poster. But you can find that at tinyurl.com/JZQ DR40.
Yeah, we'll probably put a link up to that on our Twitter as well and our Facebook. Cool. So yeah, so this episode, for those who are interested, is based on that paper. So if you listen to this episode and then if you want to hear more, go to that paper or read them at the same time. Well, actually, you shouldn't do it at the same time. That's hard.
Yeah, and while you do that, you can, compose a concerto.
Yeah, why not? Looks like in this episode we have quite a few things we're going to do. We're going to talk about our story so far, specifically with respect to climate science. We're going to talk about how global average temperatures have changed in this last century. We're going to talk about some models. We're then going to go to talk about the data and the tools and how we know what we know.
And then we're going to go over some properties of radiative energy as a whole. Radiative energy meaning energy that's carried by photons or other particles.
This gets real meaty. Yeah, we're going to really get into the meat of physics here.
Oh, yeah. This is all very concrete stuff. And then we're going to be talking about some properties of gases and how they absorb energy. And then we're going to talk about some models of global warming.
Yep. So both simple models as well as improved models with more information and more mathematics and just how our knowledge about greenhouse gases changes.
As well as the difference between the types of models and what is useful for what and why we need more advanced models and why we don't.
Yes. So this will be a thoroughly meaty episode. So according to the resource from Harvard, it was harvard.edu.
Edu, yeah.
Okay. So it looks like just in this last century alone, the average global temperatures of the Earth have changed by 0.5 degrees Kelvin, and they have changed positively. We've seen a increase of 0.5 K.
And while that might not seem like that large of a change, you got to remember that the difference between now and our last ice age was only 4 Kelvin or so.
Yeah, that's insane. So, and again, just knowing what happened in the last ice age, like.
Yeah, like slabs of ice that were over New York that were like about a mile thick.
Yes, yeah, absolutely. So how? Oh, and also,
and 1 to 5 Kelvin of climate change, positive climate change is expected in the century to come, depending on how quickly we act.
Yes. Now, real quick, so is that the conservative estimate? Because I've heard 1.5, I've also heard 2, and I've heard more than 2.
Oh yeah, this is 1 to 5 is kind of the range.
Okay. Oh, 1 to 5. Oh, I read that as 1.5. So how do we know this?
Well, I mean, there's models that we're going to go into later, but the models all kind of treat the Earth as basically a substance, or not even a substance, just like an object that has energy and can absorb and reflect energy. And it treats the atmosphere. It treats the atmosphere as something that can absorb and reflect energy, and treats the Earth as something that basically reflects ambient energy. There's also models of the Earth which actually take momentum of like airflow into consideration and all kinds of things.
Oh wow!
But we got to consider how we know that models are accurate, and we know that it's accurate if it generates data, like present data from past data, or if it generates a trend from a small sample of the data.
Right. So basically what we're saying is we have a model, and according to this model, it'll show a temperature trend. We have recorded temperature data for the last 100 years, 150 years,
something like that.
Okay, and then if this model, we can do is it a retrofit, like a reverse fit kind of thing?
Yeah, like we could like put in the atmosphere 100 years ago, and if it generates the trends that actually have existed throughout the last century, then we know that it might be an accurate model. Mm-hmm. However, there's also the problem of overfitting a model, which is where a model just fits the past very, very well, but has no correlation to the future. Mm-hmm. And that usually happens when you put in a lot of variables into a function, like not necessarily just a lot of variables, but a lot of constants that are hard to change or that mean specific things. And these can even be embedded in the math sometimes.
Mm-hmm. So models can certainly be a tricky thing with complex systems. That's for sure. But I mean, it's kind of the same thing with like globes. Like, any globe that we have is like a perfect sphere. Well, we know the Earth is not a perfect sphere. The Earth is, what is a spheroid?
Oblate spheroid.
An oblate spheroid. Not only that, but as you increase the resolution, there's all kinds of rocky things, and like it's every single model that we have is just a tool for us. They are not perfect.
Absolutely.
Yes.
Yeah, a perfect model would be a replica of the Earth and the Sun and every star, and it would just be a completely separate universe that we'd somehow interact with.
Yeah, which is
and the model would completely go out of it would stop working immediately, though, because our universe would start to be based on that model.
Yes. So a very valid scientific question is, how useful are these models? And I've heard a lot of critiques on models. Like if you're watching Fox News or something, they always have people on there who love to rag on the models. There's a reason why these models haven't been thrown away. These models aren't useless. They are extremely good. They are extremely useful. And we're gonna get into the nitty-gritty of them and talk about what they're useful for, as well as the shortcomings of them.
And also the reason why these models that we're going to be discussing today are very useful is because the more the models have been refined, the more predictive power they have gotten. But not only that, it's not like we invent new models and then we come to some radically different conclusion. It's not like 50% of models don't show global cooling and the other 50% show global warming.
Correct.
They all are in consensus with one another.
Yep.
And from the simplest model to the most complex model, we see the same thing.
Mm-hmm. You mentioned a potential problem with this called the telephone game. Can you elaborate on that in the outline?
Oh yeah, I mean that's just what I put in the notes. But what I meant by that is, if a model just agrees with one other model, which just agrees with one further model, then you can have like so many degrees of separation between the models that you're using a justification to justify justification that's justified itself by justification. But that's why a scientific consensus where studies support one another is important. It's almost like moss. The stronger it is, the more interwebbed it is.
Yes. Now, at this, there's a URL here that we have in the website. This is the one that you gave earlier. Is that right?
Yeah, and this has a lot of this information on it.
Okay.
And you could actually use it almost as a reference to this episode until we have the we're going to put a reference to once we finish the paper in about a week or so. Mm-hmm. We're going to put a link to it at the beginning of the episode. We could do that now with Anchor. Mm-hmm. So yeah, so just take a tinyurl.com/JZQDR40 with a grain of salt.
That website has a discussion of the models that we just previewed, correct?
Oh yeah, very in-depth and a lot of formulas and stuff.
I can imagine a lot of our listeners would like to go more in-depth on the models. Even our listeners who may be skeptical of climate science, at least for a resource to see what information we have on the models and their shortcomings.
Oh yeah, I encourage any skepticism, and I encourage it to be met with scientific inquiry.
Yep. Absolutely. And also, it is worth noting, we said this earlier, but this website that we gave you, it has further resources linked to it. However, you're going to find a few things that aren't quite refined, such as which is usually millimeters, instead of micrometers. So watch out for that.
Yeah, and like little things like that. It doesn't explain certain elements of the aspects of the tool extremely well, but what are you going to do?
So let's talk about the data and the tools that helped us to get that data for what we know about our climate and our Earth's history.
Yeah, and what's interesting is that apparently there is actually a natural fluctuation in the Earth's temperature that's occurred since the 1700s. And the global temperature has actually been occasionally higher than it is now. But the thing is it hasn't increased as quickly as it has now. But given the graphs, it is sometimes hard to see it's hard to see a distinctive human-caused trend just visually. And that's why we need tools to inspect. I mean, there are certain graphs that show it pretty distinctively, but I'm just saying that if you look at the temperature itself, you could come to some very reasonable conclusions.
Yeah, and actually, you just said something before. I have heard the same. I've heard this, on certain shows on TV, on certain news outlets where they talk about it's been hotter before and life thrived. Where you had dinosaurs. Like as far as certain parts of the northern hemisphere where they wouldn't be able to live now. However, the rate of change is the kicker here. And if you want to know a really, really good resource that really illustrates the rate of change, there is an XKCD comic strip that does this very, very, very well, where it lays out what Earth has been like for the last 20,000 years.
Yeah, and you can find that at xkcd.com/1732.
Yes. One criticism, especially from my friends, has been, this is just a comic. You can make a comic of whatever you want. Right. Well, this comic actually has its references in it as well. If you look down the right side of the comic strip, there are 4 references, including the 2013 IPCC report as well. So,
wait, did they really say that because it's a comic, it's just because of that? It's even though it has resources, that's like saying that you can't do accounting on anything but clay slabs, because that's what I grew up with.
Yeah, sure. So, but yeah, this shows a fantastic illustration of the rate of change, where it starts off at 20,000 BCE, and we see, I believe it is global average temperature at -4 degrees Celsius to what it is right now. And then it shows a real gradual increase as the ice age ends. And if you keep scrolling down, it's just a very, very, very gradual change here. Very gradual change. And then toward the very, very end, you have human involvement, and suddenly it ramps up. I don't want to say exponentially. That may not be the correct mathematical term here. It's a sudden jerk upward very, very, very fast in terms of average global temperatures.
I mean, there's a lot of measurements of and people might be like, how do you know, how do we know how hot the Earth was 15,000 years ago? We have ice core measurements, we have tree core measurements, we have
coral data. We have so many things. That's what we talk about as scientific consensus. It's not like we have one study or one type of study that says this. It's many. Yeah, I think in a lot of the papers, you'll read about the term proxy data, where you don't have an actual thermometer, but oftentimes you'll have data collected from, for instance, tree rings, and they will correlate the data with what we do have in our temperature record. And if you see, a significant correlation, then it's assumed that correlation exists backward in time as well.
Yeah, I mean, you could think of it as a picture of a blurry thermometer.
Yeah, pretty much.
So we're going to talk about radiative energy a lot, because the sun radiates energy onto the earth, and the earth radiates energy outward when it's hot. And it's measured in watts per square meter, which is power per area.
And measuring the radiative flux for each wavelength and summing it up gets the total radiative flux.
And but the radiative flux is different at each wavelength because, okay, let's say we get a piece of iron, right? And we heat it up. The first color it turns is red, right?
Yes.
Because it's emitting, and an iron is almost like a blackbody. So Actually, we'll just talk about black bodies to typify this or exemplify this, something like that. So it turns red first because it's generating a lot of heat, but also a few red photons, which are low wavelength photons. And then it turns yellow because it starts getting yellow and green wavelengths, which combine with red to make yellow in our eyes. And then as it gets more and more wavelengths, it gets whiter and whiter. So that's for a black body. But a black body is a perfect object that can absorb every wavelength and emit every wavelength. But we know from experimental data that if an object can absorb a wavelength, then it can emit it just as efficiently as it absorbs it.
So there's something that I'm going to talk about called the flux distribution for a black body. The flux distribution for a black body was discovered by Max Planck in 1900 by the equation. This is a bit of a wordy equation here. If you don't have to take notes on this, this is something that you can just Google search. But the equation that he found was 2 times pi times Planck's constant times c squared.
Which is the speed of light squared.
Correct, speed of light squared. All of that divided by L, which we just mentioned above. I don't think we actually
wavelength,
said it.
yeah.
Yes, L is the wavelength to the 5th power times e raised to Planck's length times the speed of light. All divide by Boltzmann's constant times the temperature times the wavelengths.
And that's all over that's all over E.
Yeah, I fully get. And then there's a minus one. Did y'all get that? Did everyone get that? Okay, we're good. Just Google search it. Just Anyways, yeah. So there's an equation here that exists, and the peaks of this this shows that peaks at wavelengths are inversely proportional to the temperature.
Yeah. So if it's a really really high temperature, then it peaks at a very short or very very energetic wavelength.
Correct. Yeah. All of that math just to say that single point. If the object absorbs a certain percentage of radiation at some frequency, then it will also radiate at that ratio.
If you absorb like 50% of red light, then what that means is that when you're heated up, you will emit 50% as much red light as a black body would emit.
This can allow us to generate the emission spectrum from the absorption spectrum. Literally multiply the absorption spectrum by the black body radiation spectrum component wise.
Like over the frequency. So you have the first graph, which is the black body radiation spectrum, which goes something like woo over time. And then like you might have the absorption spectrum, which might be actually very like abrupt, like no, nothing, and then 1 for a little bit, then half for a little bit. And the absorption spectrum, especially with the atmosphere, is something that's going to be very messy. And if you multiply the two, then you get the emission spectrum, what it emits when you heat it up. And that's essential for climate science because the energy emitted by the atmosphere and the Earth is what it's heated.
Correct. Yeah. Actually, that's the main point of this. So that now that we've talked about how you can know the emission spectrum or the heat or the energy that objects radiate, if you know that based on their absorption spectrum and vice versa. If you know the absorption spectrum, then you know the emission spectrum. So now let's talk about 2 very specific bodies that relate to climate science, and that is the Earth and the Sun. What do we know about the Earth and the Sun?
Not much. I'm just kidding. Solar radiation peaks in the visible range, which is not surprising because we're designed to look at things that reflect solar energy, which is about 400 to 700 nanometers. And it's maximum in the green, which is 500 nanometers. And about half is at infrared frequency, which is less than 700 nanometers. And a very small fraction is in UV. So this is the composition of the sun's energy. It just tells us what we know is like about half is like in the infrared, which is very closely related to heat. And the reason why infrared is closely related to heat is because gases, as we'll see in a second, absorb infrared radiation by either rotating or vibrating. Yeah, we'll talk about that in a second.
Yeah, actually, that's something I found very, very interesting. Is I had no idea. Like, we talk about emissions and absorption. I didn't know what happened at an individual molecule level. I guess there's all kinds of interactions, including vibrations, where I think of like a spring. Like if a molecule were to spring, it would squish and expand, right?
Oh yeah.
Not just in one direction as a spring does, but in multiple directions. But then there's rotational energy, where you've got something like spinning around. Like I think of rolling down a hill, and you get all kinds of heat there.
Or if like somebody's playing tennis and they put a spin on it.
Yeah, exactly. So there's all kinds of things related to heat at the individual molecular level. Fascinating stuff, I find, actually. Now, we know that the Earth is not sufficiently hot to emit significant amounts of radiation in the visible range. We know that because it's not like a lump of coal that glows red in a fire.
Yeah, if you looked at, I mean, sometimes the Earth glows red like at volcanoes, but that's pretty much it.
Yeah, that's not saying the Earth
no, not the
itself
surface
as a whole. Yeah,
that's a very dramatic explanation of why it doesn't, like how we could see that it doesn't emit significant amounts in...
Yeah. Now, by the laws of thermodynamics, everything radiates. So the Earth certainly does radiate. It's just not, I mean, as long as it has any motion whatsoever, it radiates.
Any heat whatsoever, I believe. And I think motion might be related through some kind of, I think Hawking studied that black bodies that are traveling through space have a slightly different temperature. I'm not sure.
Yeah, interesting stuff. Yeah, learn more about that in our black hole episode, where we literally talk about the thermodynamics of black holes. Fascinating stuff as well. This is not nearly as complicated.
No, not nearly.
Yeah. So,
although the models themselves are more nitty gritty, as we will see, I will have to say that for them. But yeah, the math itself is very basic.
Now, let's talk about the thermal equilibrium of the Earth and the surrounding space.
Oh, yeah. So basically, if the Earth is at a constant temperature, thermal equilibrium is when the amount of radiative energy going into the Earth from the sun and stars and everything is equal to the amount of radiative energy, which is the almost microscopic amount of visible radiation, as well as very large amounts of infrared radiation emitted by the Earth are equal. The amount of energy that is reflected is very important. It's a property called albedo. And it's reflected back into space by clouds, snow, ice, whatever. And it's equal to 0.28 for the Earth, which means that 28% of the light that reaches Earth is radiated away. In the IR range, though, it's almost 100%.
Interesting. Now, this is something that we'll talk about more and more with, again, as you said, with Earth, the albedo, or rather the amount that is radiated back into space is A equals 0.28. For other planets, it's completely different.
Yeah, and what's interesting is that the mean temperature of Earth, because of the albedo of the Earth, and this is a very simple equation. This doesn't relate to temperature within the Earth, but it's 255 Kelvin, which is about negative 18 degrees Celsius, or I think negative 25 Fahrenheit or something like that.
Okay, I don't know. I'll have to. I'm not doing the math in my head right now.
Yeah, me either.
Perhaps. So, what about something like Venus?
Now, Venus, which has a famously hot atmosphere that can melt, I believe, lead. Can it? Yeah, it can melt lead. So even though it can melt lead, it has an average temperature of negative 41 degrees Celsius, or 232 Kelvin. And you might wonder, how can this be? And the reason why is because of all the clouds on Venus. They reflect out about 75% of the light that reaches them.
Wow, interesting. So here's the thing, though. So if it's reflecting that much light, if it reflects 75%, it's closer to the sun than the Earth. Then yet it's still hot enough to melt lead. Yeah,
and the reason why is because of the difference between the ground temperature and the atmospheric temperature. That's represented by a separate model, as we'll see in a second.
Okay.
And I think it's interesting because like we said, it's 700 degrees Celsius, or 500 or something like that on the surface of Venus. It's hot enough to melt lead.
Wow.
But its average temperature is negative 41 degrees Celsius, as seen by an observer in space.
Wow, interesting. So higher albedo still would mean if it were a lower albedo, it would be even hotter.
Oh yeah. Well, not necessarily on the surface though, because because lower albedo might mean that the composition of the clouds are different, and clouds are actually one of the biggest varying factors in climate models.
Absolutely. So now that we've talked a little bit about radiative effects, as well as the Earth and the Sun, it's time to talk about something else, namely gases.
Yeah, and why are gases important? Because the atmosphere is made of gas.
Yep, exactly. So, a few things about gases. First of all, the internal energy in a gas is quantized in a series of electronic, vibrational, and rotational states, at least according to our current understanding. Increase in internal energy corresponded to a change in state. Now, this is where it gets...
And right away, and that's a current, Gabriel mentioned current understanding, and I wanted to expand on that. That's a current understanding according to even the standard models. So.
Yes, yeah, so that's pretty solid. When I say that, it's not like it's going to change, next
year.
It could.
It could change next year.
But according to the standard model, that is basically as rigorous as it currently gets. That, again, this is again, you learn something new every day. This is something that I was unaware of. Each of these three quantized modes of a gas corresponds to a different amount of energy. For example, in order to increase the electronic energy of a gas, am I saying that right?
Oh, yeah, the electronic internal energy in a gas.
You would do that through applying UV or ultraviolet radiation to it.
And this is actually interesting because one of the early experiments in quantum physics was charging gold foil using UV light and showing that it can't be done even with a ton of red light because of the... we go into this more in detail, I believe, in... do we go into detail in that in the black hole episodes?
I don't. We should. If we didn't, we should have.
Listen to the whole thing to just check.
Listen to everything we've done and come back to us. How's that sound?
But finish the episode now.
Yeah, okay. yeah, exactly. Yeah.
But, then for vibrational changes in energy, you need near infrared energy, which is like very, very low red to 700 nanometers to 20 micrometers.
Correct. Yep. And that's just, again, the should we call it, lack of a better term, the springiness of the individual molecule?
Yeah, the buzziness, springiness.
Okay.
How much they vibrate.
Sure. And then lastly, you have the rotational energy. If you want to change the rotational energy of a molecule, then you'll have to apply something greater than 20 micrometers. So that's far infrared?
Yeah, far infrared. I believe that is related to how microwaves work, actually.
Okay. I mean, you could blast even radio waves, like lower frequency radio waves, and then change the rotation of molecules.
Yeah.
So interesting. And then it says here that visible changes... there's nearly no changes in visible light of them. Is that's?
Oh, what's interesting is that the visible spectrum doesn't cause many changes in gas states. It doesn't change UV. It doesn't change electronic internal energy, nor does it change vibrational or rotational significantly.
Okay. Couple of considerations here. So if the charge is distributed symmetrically, then it cannot acquire vibrational states, since the vibrational states affect the dipole movement, which affects the structure of the molecule. Let me say that again. So you have different atoms and you've got different gases, and the valence electrons are arranged differently in each of them. There are some of them like the noble gases where you've got 8 valence electrons, right? Mm-hmm. And there's an issue here. If they're distributed evenly, then you're really not going to be able to add a whole lot of vibrational energy to it. Is that right?
Yeah. Well, let's take nitrogen for an example.
Yeah.
Nitrogen is two nitrogen molecules connected together. It's distributed. Its charge is distributed perfectly evenly, like exactly evenly. Mm-hmm. And because of that, basically it can't bend or anything like that. And mm-hmm. since it can't bend, there's nothing to vibrate really.
Yeah.
Imagine having a molecule in front of you. It's just made of little balls connected by very, very tight springs. Mm-hmm. The more you can if you did nitrogen, if you tried to twang nitrogen, there would only be one vibration, and it would be throughout the whole thing. Mm-hmm. But if you did something like carbon dioxide, you could bend it back and forth, and because you could bend it back and forth, it wobbles.
Okay.
And so just the kind of wobbliness is correspondent to vibrational energy.
So basically, again, you're going to have different shapes based on the arrangement of electrons, and some of these shapes have more vibrational energy than others. And that
or more receptive to vibrational energy.
Correct. Yes, and that includes carbon dioxide.
Yeah, and molecules that can acquire a charge asymmetry mm-hmm. by stretching or flexing. So actually, let me do carbon dioxide as like a counterexample. So carbon dioxide has two carbons on either side, two oxygens on either side, one carbon in the middle. So it has like the negative charges on the outside and the positive in the middle. So it's perfectly symmetrical. So in that state, it can't acquire any vibrational energy. However, if it gets knocked out of that state, like for example, if the carbon gets closer to one of the oxygens just perchance, or it bends in the middle, kind of like a joint, then it can acquire more vibrational energy in that state. And so those are greenhouse gases. So hydrocarbons, O3, N2O, H2O, carbon dioxide. And H2O, although water is a greenhouse gas, it's a very, very short-lived one. As we'll see, that affects how potent of a greenhouse gas something is.
Yeah, and as you said earlier, molecules that cannot acquire charge asymmetry by flexing or stretching, things like N2, O2, or H2, are not, therefore, greenhouse gases.
And the efficiency of absorption in our atmosphere is actually about 100% in the UV due to the electronic transitions of oxygen and O3 in the stratosphere. And it's about 100% in the infrared because of greenhouse gases. But between 8 and 13 micrometers, near the peak of terrestrial emission, there's like a weak window between 8 and 13 micrometers, but like a peak for O3 at 9 point. So basically, it's a complicated atmosphere is what we're saying. And you need models that reflect this. But we can go and do some simple models too.
Yes. So with all that said, this is the part that if you've made it this far on the podcast, let me just say congratulations. You've been listening well or just playing it in the background. For this next part, we're going to talk about a simple model.
So a simple model, we start by pretending that the atmosphere is like a shell above the surface of the Earth that can absorb energy.
Yeah, I mean, it already is above the Earth, but what we're talking about is like separate from the Earth.
Yeah, like imagine...
Like a ring?
Yeah, imagine like you got rid of the white part of the shell of an orange, and all you're left with is that orange on the outside and the fruit on the inside. That's kind of the model we have.
Sure. Okay. Cool. So yeah, in this simple model, it implies something, or it implores something that we call Kirchhoff's law. As an electrical engineer, we use Kirchhoff's law, but it's used in many things about the flow of energy. Kirchhoff's law basically states that the electricity the current that goes into a node is going to be equal to the current that leaves that node. They have to be the same. It's sort of a conservation law, if you will.
Yeah, and it applies and it applies here because we were saying that the shell that the atmosphere is pumps energy outwards and inwards, outwards towards space and inwards towards the Earth.
Correct. And they have to be, what goes out has to be what comes in, and vice versa.
And we also have a sun that is giving a constant amount of solar radiation.
Mm-hmm. So in this simple model, if we were to calculate the incoming solar radiation, we would simply have to add the energy that's radiated from the atmosphere into space, that's the outer layer, plus the energy that's radiated from the Earth into the atmosphere. Again, in the simple model, the atmosphere is above. So it's Kirchhoff's law. What comes in from the Earth is equal to what is absorbed outward.
And we know the amount that is radiated from Earth into the atmosphere and from atmosphere into space, because as we mentioned before, the amount that's absorbed is the fraction absorbed is the fraction radiated. Mm-hmm. And we use Kirchhoff's law also to show that the temperature of the amount of energy absorbed by the atmosphere from the Earth's surface temperature is equal to the total amount of energy being irradiated away from the atmosphere, both into space and into Earth. Mm-hmm. And we'll have more details on that in the paper to come.
Yes.
But basically, we get this formula that the temperature of the Earth is equal to the mean solar flux times 1 minus the albedo, all divided by 4 times times sigma, which is a constant that relates the fourth power of temperature to a black body's energy. So we're assuming that the atmosphere is a black body. This is called the gray atmosphere model. Mm-hmm. So it's over 4 sigma times 1 minus f, which is the amount of the fraction absorbed by the clouds, divided by 2, all to the 1/4. So as you can see, if we change the fraction that is absorbed, and we might have an app where you can play around with this. Actually, it'll change the temperature pretty significantly, which explains why Venus, even though it's colder than the Earth, is hotter at the surface.
That'd be a very cool app, actually.
Yeah, and so we showed that the global surface temperature is about 288 Kelvin,
which is what, Fahrenheit?
I think it's like 40 or 50 degrees.
Okay, well, yeah, we can do a quick.
Yeah, it's like 58 degrees.
Cool, very good. Right on. Let's talk about, obviously, there were some simplifications made in that model. We have improved models as well.
Yeah, for example, when we were calculating the previous thing, the amount of energy absorbed by the atmosphere from the Earth's surface temperature and stuff like that, we could have looked at how it affects every single different spectrum differently, and then sum it up together. That's something that we did not do. We just assumed that the Earth was black and then the atmosphere was black.
Yeah. So basically what we're saying is the model can be improved by not considering the Earth and atmosphere as black bodies, and still improved further with something called GCMs, or general circulation models. Basically, those provide 3D equations for energy, mass, and momentum. Man, that gets real mathy. For those of you guys who like spaghetti of math equations, this is right up your alley. You'll love this.
Oh yeah, but what's interesting though is that this model that we're talking about here, you can see in the link that we linked to earlier, that it actually predicts a slightly more global warming than we've had in the last century than actually happened, but it's still pretty fairly accurate, even this small, like almost insignificant model.
Yeah. So the simple models are still very, very good,
and they only get more and more specific. It's like we're just getting more refined models now.
Yeah.
And like with the GCMs, the general circulation models.
Yes. You know, I have it on good authority that some of our listeners might be like us, fairly nerdy, and they like the nitty-gritty details. Should we tell them some more of the points that are in the more advanced models?
Yeah, well, basically, it's one of the more nitty-gritty points that it has in that thing is optical depth, which is how much flux is absorbed and scattered over time. You could take the different layers of the Earth's atmosphere, the stratosphere, ionosphere, troposphere, and I think thermosphere. You could take all of those into consideration. Like, there's so much stuff you could do. Like, the world is your oyster when it comes to this stuff.
Yeah.
But what's interesting too is that although there are disagreements in the predictive surface warmings resulted from an given increase in greenhouse gases, all GCMs tend to show a linear relationship between the initial radiative forcing and the initial ultimate perturbation to the surface temperatures. Let's break that down. What is radiative forcing? That is just the radiative perturbation associated with an increase in a greenhouse gas. So it's saying if we add 1 pound of carbon dioxide to the atmosphere, how much radiative energy increase are we going to see at the surface? And we relate things to carbon dioxide because it's a kind of a baseline, and also I think it's the most prevalent greenhouse gas. But I mean, methane is over a period of 20 years is 62 times as potent as carbon dioxide as a greenhouse gas. Over 500 years, though, because it has a short lifeline, it's only 8 times as potent. But if we want to look at a really potent greenhouse gas, check out sulfur hexafluoride.
Oh, wow. What do we have for that one? Let's see.
A lifetime of 3.2 millennia. In over 20 years, it's 16,500 times as bad as carbon dioxide, 24,900 in 100 years, and over 500 years, 36,500 times as potent as carbon dioxide.
Wow, that is insane. So basically what we see then is over a 100-year time horizon, reducing use of sodium hexafluoride emissions by 1 kilogram is as effective from a greenhouse perspective as reducing carbon dioxide emissions by 24,900 kilograms. That's important for designing regulatory goals.
And another important, I mean, and also we can't just, if there's only 1 milligram of sodium hexafluoride released into the atmosphere per year versus 1 billion pounds of carbon dioxide, we still have to pay more attention to carbon dioxide. So that's not the actual stats as you might have guessed, but it's something to take into consideration. And that's how it can help us design better factories. And once we have regulatory goal points when it comes to greenhouse gases and the amount we could even design factories in terms of radiative forcing, tax them in terms of how much radiative forcing they generate. Like, there's so much stuff we can do with this data. And I think that's a big takeaway from this. Oh, and these are the models which tell us that we are generating enough carbon dioxide to create a significant effect. As we've seen, global warming is happening, and we are mostly to blame.
And actually, I believe that, if I'm not mistaken, humanity is entirely responsible for the current warming, as we should actually be in a cooling trend.
Oh, I did not know that. We have learned about how radiative forcing relates to climate science, how gases interact with light, and what we might be able to do about it. I'm Sophia.
And I'm Gabriel.
And this has been Breaking Math. Just a reminder, we are on patreon.com/breakingmath. and facebook.com/breakingmathpodcast, where you can see new releases, things like that. breakingmathpodcast.com. What else?
So this has been a very exciting series for me. We have interacted with some real top level researchers. I'm not sure I'm at liberty to say who we've been chatting with.
We'll save that just in case it doesn't pan out.
Absolutely, yeah. If this topic is a huge topic the world over, with the Australian wildfires that have been exacerbated by climate change, to
California fires,
flooding in low-lying areas, all kinds of things.
I mean, even Syria can be attributed in a large part to the rapidity of climate change.
Correct. If it changes the allocation, if it changes the availability of natural resources, then it'll have an impact on things like
economics. Because I mean, if you want to see how, if you want to watch something, I would check out by CGP Grey. It's on YouTube. It's The Rules for Rulers, and it talks about how resource distribution can lead to either democracy or tyranny.
Correct, absolutely. So yeah, and on our Twitter recently in the last 6 months, I have followed probably 24 climate scientists, including people like Dr. Catherine Hayhoe, lead author of the U.S. Climate Assessment from 2018, also Dr. Michael Mann, as well as a slew of others as well. So send us your climate change related questions and questions for any of these doctors, and we'll see if we can find answers to them.
I'm Sophia,
and I'm Gabriel,
and you're listening to
Baking Math.